Good day, I'm Norman Wobbeker. Today we're going to extend the very familiar arithmetic with rational numbers to a wider setting where infinity appears. But the infinity that we're going to introduce is not at all abstract or philosophical. It's actually just very simply tied down to the geometry of the plane. So the rational number system, of course, is for us a absolutely fundamental arena for doing mathematics. In my view, the rational numbers are the core of arithmetic, and almost all of mathematics is somehow linked to the rational numbers. The real numbers play a very dubious role as far as I'm concerned. So the rational numbers with the four familiar operations, addition, multiplication, subtraction, division, is an almost perfect arena for arithmetic, but it's not quite perfect. The reason is that division by zero is not allowed. And this, of course, is a very common source of errors in mathematics, because it's very easy to forget when you have a fraction or a rational number to check that that denominator is non-zero. So what we're going to do today is we're going to look at the very familiar framework that we've already established: natural numbers, integers, fractions, and rational numbers. We're going to think about extending that now to this sort of larger framework by introducing more formally the arithmetic of integral points. We've already talked a little bit about that in our last video. We're going to extend that discussion. And then we're going to use the arithmetic of integral points to introduce the extended rational numbers, which is essentially the rational numbers where we adjoin infinity. And then the possibility emerges that we can think about rational number arithmetic not by going from the integers to the rational numbers directly, but rather by going through this admittedly longer route, by going from the integers to the integer points to the extended rationals and then to the rational numbers. In other words, we'll see the opportunity of being able to think of the rational numbers as just a sub-framework of this larger and perhaps more fundamental framework, the extended rational numbers. So these are somewhat unfamiliar ideas. If you're a professional mathematician, you may feel sort of the ground wobbling a little bit underneath your feet. But from a geometrical point of view, this approach, I think you will see, is very natural. Although the implications for arithmetic and analysis, I think, are still waiting to be worked out. We have a lot on our plate to do, and I'm going to leave a number of things for you to do. So there'll be quite a lot of opportunity for you to get your hands dirty, roll up your sleeves, and get to work making computations and checking things. So we've already talked last time about the integral points. These are just pairs of integers enclosed in square brackets. And we introduced a couple of operations with these objects. First of all, we defined scalar multiplication, what it means to multiply an integer point by another integer. So C times the point AB is the new point CA, CB. We call this scalar multiplication. And then we had notions of rational addition and rational multiplication. So the sum of AB and CD is AD plus BC, BD, while the product is AC, BD. Today we're also going to introduce two new operations: rational subtraction and rational division. So we have all four operations defined on these integral points. Rational subtraction looks a lot like rational addition, except instead of having a plus sign here, we have a minus sign. So it's AD minus BC, comma, BD. And rational division looks a lot like rational multiplication, except that the role of D and C are interchanged. So AB divided by CD is AD, comma, BC. And we're going to use these notations for our operations. The plus and the minus, or the addition and the subtraction, are going to be enclosed in a circle to distinguish them from the more familiar addition of vectors or subtraction of vectors. The multiplication and the division are not going to have circles around them because there is no standard multiplication or division for vectors or points normally anyway. So these are somewhat new operations. But we don't want to confuse these addition and subtraction operations with the addition of vectors like a, b plus c, d is a plus c, comma, b plus d. That's not what we're doing here. And let's emphasize that all these operations require only integer arithmetic. They're always defined, doesn't matter whether some or all of the integers involved are 0. Okay, so we're working purely with integer arithmetic, and we don't in fact even need to know any rational arithmetic here. So in principle, what I'm doing here could have been introduced much earlier in this series. Just after we introduced integer arithmetic, we could have introduced this arithmetic of integral points. One more concept that was useful was the notion of the height of a point. So the height of the point AB is the second coordinate B. So now we have 4 operations defined on these new objects, these integral points. So in our last video, we talked a little bit about some of the main laws involving addition and multiplication. So I remind you what they are. Here are the commutative laws. Here are the 2 associative laws. And then we had these rather unfamiliar distributive laws, where we have to multiply this expression by the height of p in order for this side to equal the familiar p times q plus p times r. And the other way around, we have to multiply this side by the height of r in order for this thing to be equal to p times r plus q times r. And although this is unfamiliar, it is in some sense more balanced than the usual one, because the p appearing twice on the right-hand side is now also appearing twice on the left-hand side, which means that this is somehow homogeneous in an important way that will be significant later on. So these are familiar from last time. Now we're going to introduce some more laws because we have these 2 new operations of subtraction and division. So these are sort of associative laws, these 3 here. P plus q minus r equals p plus q minus r. P minus q plus r equals p minus q minus r. And p minus q minus r equals p minus q plus r. And I'm going to leave it to you as an exercise to prove these. So you can write down proofs by, well, setting p equal to AB, q equal to CD, r equal to EF, for example, calculating the left-hand side, calculating the right-hand side, showing that they're in fact equal. And here are 2 examples that illustrate a couple of these laws. So for example here, this one illustrates, I suppose, this one here. So 2, 3 minus 1, 4 plus minus 1, 1. That's the left-hand side. And over here we have the right-hand side, 2, 3 minus 1, 4 minus 1, 5. And let's just check this last line. What does it say? So 2, 3 minus 1, 4, how do we compute that? 2 times 4 minus 3 times 1. That is 8 minus 3, that's 5. And then the second entry is just the product, 3 times 4, 12. We have to subtract minus 1, 1. How do we do that? 5 times 1 minus 12 times minus 1. So that's 5 plus 12, that's the first entry. And the second entry is the product of the last 2, is 12. Right, so we can check these laws in special cases, which is a very good thing for you to do. We also have some associative type laws involving multiplication and division. For example, p times q divided by r is the same as p times q divided by r. P divided by q times r is P divided by Q divided by R. And P divided by Q divided by R is P divided by Q times R. And again, I'm going to leave the proofs of these things as exercise for you to do. Let's just have a look at this last one here. In the case of 3, 4 divided by 0, 2 divided by minus 1, 5. So that's the same as 3, 4 divided by, this thing divided by this means the first entry here times the second entry here, which is 0 times 5 is 0. Then comma, the second entry here times the first entry here. That's minus 2. And then this divided by this will be this product, which is minus 6, comma, this product, which is 0. And if we do it the other way around, the right-hand side would be 3, 4 divided by 0, 2 times minus 1, 5. So this quotient is 3 times 2, 0 times 4, and then we have to multiply by minus 1, 5. That's just multiplying the corresponding elements. 6 times minus 1 and 0 times 5 is 0. So these are simpler than the addition, subtraction, associative laws. And interestingly, these laws have exactly the same format as the previous ones with addition and subtraction. So if you replace the multiplication and division with addition and subtraction, then these have exactly the same form as the ones on the previous slide. And we also have some more distributive laws. So if we combine multiplication with subtraction, we get distributive laws that are exactly the same as the ones involving multiplication and addition. So P times Q minus R times the height of P is P times Q minus P times R. And the other way around, P minus Q times R, we have to multiply by H of R, and then we get R times P minus Q times R. There's also distributive laws involving division, just as there are for rational numbers. But division is not quite as symmetrical as multiplication, so there's not two sets of laws. There's only laws involving expressions like P plus Q divided by R or P minus Q divided by R. So here the expression is P plus Q divided by R times L of R equals P divided by R plus Q divided by R. What is L? Well, L represents a new object, the length of an integral point. We'll just define that to be the first coordinate. So the height is the second coordinate. Let's say that the first coordinate is the length. And so that's the number that we have to multiply by here to preserve the homogeneity when we're dividing. And the same law when addition is replaced with subtraction. So let's give an example here. First of all, please prove these. And here's an example. So we have 2, 3, minus 1 minus 1 divided by 5, 4. So when we calculate all of that, that's the left-hand side, we should multiply by the length of R. The length of R here is 5. All right, so what does this become? It becomes 5 times. The 2, 3, minus 1 is minus 2, minus 3, so that's minus 5, followed by minus 3, divided by 5, 4. And so that's altogether 5 times. This divided by this will be the minus 5 times the 4, which is minus 20, and then the minus 3 times the 5, which is minus 15. On the other hand, 2, 3 divided by 5, 4, minus 1 minus 1 divided by 5, 4. What's that? Well, this quotient is 8, 15. It's that product, followed by that product. And this quotient is the 1, 4, followed by the minus 1 times 5. So it's 4 minus 5. So we have to subtract these two. How do we do that? It's 8 times minus 5 minus 15 times 4. So minus 40 minus 60 for a total of minus 100. Followed by the product 15 times minus 5 is minus 75. And this are the same because 5 times this is just minus 100 and minus 75. There are also some special integral points, ones that play distinguished roles. Just as in the rational numbers, we have some special numbers, primarily 0 and 1, and also minus 1. So here are some laws that involve special integral points. The point 0, 1 acts as 0 additively, so when we add it to any integral point AB, we get AB. The point 1, 1 acts like the number 1, so 1, 1 times AB equals AB. 0, 1 times AB is 0B, and this number 1, 0 also plays a role, a new kind of role. That's what we're going to be calling infinity shortly. So 1, 0 times AB is A0, kind of complementing, multiplying by 0, multiplying by this sort of infinite element has a sort of complementary aspect. When we add 1, 0 to AB, we get also B0. B plus 0, comma 0. And then there's this other element, this new object, 0, 0, which is the central integral point. And it has the property that when we add it to anything, we get 0, 0. When we multiply it by anything, we get 0, 0. In fact, also when we subtract it or divide it by 0, 0, we get 0, 0. So AB minus 0, 0 is 0, 0, and AB divided by 0, 0 is also 0, 0. So any operation involving 0, 0 outputs 0, 0. Also AB minus 0, 1 is AB. That corresponds to taking a number and subtracting 0, we get the number back. Taking a number dividing by 1 gives the number back. If we take AB and we subtract 1, 0, this is like subtracting sort of an infinite object, then we get minus B0, which is also another infinite object. And AB divided by 1, 0 is 0B. And finally, the relationship between sort of 1 and minus 1. If we take 1, 1 and we add minus 1, 1, we get 0, 1. So this is a pleasant new domain for arithmetic. We're doing arithmetic very precisely with the integral points in the plane. And it's parallel to rational number arithmetic, but it's not quite. It's a separate thing that stands purely on its own. And it's quite a pleasant thing because it leads to this extended rational number system where we're including some new object infinity to our familiar rational numbers. So before we take the step of going from these integral points to these extended rational numbers, we have to talk about another kind of law, the homogeneity laws. And these are laws that don't have a direct analog for rational numbers. Here's a theorem, and here are the four operations, again, just to remind you what their form is. So one interesting thing about these four operations is that they're all homogeneous. That means they respect scalar multiplication, and that's what this theorem is capturing. So what's the theorem say? It says that if you take, say, any two integral points, p and q, and any integer lambda, then if you take lambda times p and you add q, that's the same thing as lambda times p plus q, which is also the same as p plus lambda q. So the multiple can be put either in front of the first point, or in front of the second point, or in front of the combined expression. All three things are equal. And why is that true? Well, have a look at the addition formula. The addition formula involves a and b right here. There's an a there, there's a b there, and there's a b there. It means that if we multiply this thing by 5, let us say, meaning we multiply both a and b by 5, then this gets multiplied by 5, this gets multiplied by 5, and this gets multiplied by 5. So both terms here get multiplied by 5, and the whole point gets multiplied by 5. And similarly, dependence on C and D, well, there's a D here, a C here, and a D here. So again, if we multiply this by some number of 5 or lambda, then this whole expression gets multiplied by that corresponding lambda. And that homogeneity, or it's kind of a linearity, holds for all 4 operations. Each of those 4 operations has the property that if we look at its dependence on just one of the points, it's linear in that point. So A, B, there's an A there and a B there. Here there's an A there, a B there, and a B there. Here there's an A there and a B there, and so on. So exactly the same logic is going to mean that the same law is satisfied by all 4 operations. Now let's see how we're going to introduce the extended rational numbers. We have these integral points and very clear arithmetic with them involving 4 operations which are always defined. And now we want to take that framework and extract from it an extended rational number system. And we're going to think geometrically, and the key idea really is the key idea of projective geometry, that if you have an affine space, like a plane, then it's interesting to think about lines through the origin. The lines through the origin form what's called a projective space associated to the affine space. So if you have a 2-dimensional affine space and you look at the lines through the origin, that gives you a 1-dimensional projective space, which is often called the projective line. So that's our motivation. And what we're going to do is the following. We're going to introduce this extended rational number framework in the following way. We're going to look at our integral points, which are represented by all these dots. And we're going to look at lines through the origin, say that one there, or maybe that one there, or maybe the horizontal one, which is very important, or maybe the vertical one, which is also very important. And what we're going to do is we're going to lump all, or almost all, the points on a line together. So what you can think about here is forming a team. We're going to organize all our integral points into teams. And all the points which are on one line through the origin are going to form one team. With a very important exception that the point 0, 0, which lies on every line, is going to be excluded from all of those teams, and it's going to form a separate team. Okay. So in projective geometry, this point 0, 0, which lies on all of the lines, always plays some sort of distinguished role. And what we're going to do is we're going to think of that as being some separate kind of object. So how are we going to do this? Well, let's have a look at this line here. So on this line there are points, say 2, 1 right there, 4, 2 right there, it'll also be 6, 3, and here is minus 2, minus 1 that lies on that line, minus 4, minus 2 lies on that line. So we're considering all the points that lie on the line, both in this direction and in this direction, but only the integral points, because we're only doing integer arithmetic at this point. And we want to lump all these points together. So we're going to refer to this line. The name of this line is going to be 2 over 1. We're going to introduce this notation by taking one of these points and writing it not as a point, but writing it as something over something else. 2 over 1. And we're going to agree that that line is the same as the line 4 over 2, because the point 4, 2 also lies on that line. And it's also minus 2 over minus 1, because that point lies on the line. And minus 4 minus 2, because that point lies on the line. However, 0, 0 is not going to be included in this equation. So we're going to be defining a new object which you can think of as being the team formed by all the non-zero points on this line. And this is going to be the name for that new team. But this is also the name for that new team. It's the same thing that we do with rational numbers. We're going to agree that this name is the same as that name. Okay, another variant. Here's another example. There's another line. It has points like 1, minus 1, 2, minus 2, minus 2, 2, and so on. And so we're going to give this line the name 1 over minus 1, or 2 over minus 2, or 3 over minus 3, or minus 1 over 1. many other possibilities. You can choose any integral point which lies on that line, which is not 0, 0, and use that to make the name for this line. There's also the vertical line. That's important for us. It has points, this one here is 0, 1, 0, 2, 0, 3, 0, minus 1, 0, minus 2. So here are various names for this vertical line. 0 over 1, 0 over 2, 0 over 3, etc. But we also have the horizontal line, which is just as legitimate a line as this line is here. And the points on it are points like 1, 0, 2, 0, 3, 0, minus 1, 0, minus 2, 0. So this line is going to have these as its names. 1 over 0, or 2 over 0, or 3 over 0, or minus 1 over 0, and so on. So every line through the origin, which passes through these integral points, will now be a new object. And then we say that we're going to treat this point here separately, so we should include it also in the story. So here it is. This point by itself is going to be given the name 0 over 0, because it's the point 0, 0. And it sort of represents a team all by itself. And this is a reasonable and consistent thing to do, because the 0, 0 element is an important and valid integral point in the arithmetic of integral points. So we cannot exclude it. It's part of the story. So this is going to be called the extended rational number system. And our familiar rational numbers are going to correspond to the lines which pass through this line y equals 1. So all the lines except for the horizontal one are going to pass through this line, and they're going to correspond to ordinary rational numbers where the denominators are not 0. This horizontal line is going to correspond to a new kind of object, 1 over 0. That's not an ordinary rational number. We can call that infinity if we like. So this new line is going to be given the name either 1 over 0 or infinity. But we're also going to have to introduce this new object, 0 over 0, which represents the single integral point 0, 0. And that's how we're going to get the extended rational numbers. A new and enlarged and maybe more beautiful domain for doing arithmetic. Worth your very serious consideration. Let's see how it looks like more officially. This is a geometrical picture, a motivation for it, but we want to set it up without any pictures. So here's our official definition of an extended rational number. And we could, in principle, have introduced this much earlier in this series, just after we've introduced integers and integer arithmetic. So before we actually introduced rational numbers, we could have done this. And perhaps on other planets in the solar system, this is how young people are taught. First they're taught natural number arithmetic, then integers, then integral points, then extended rational numbers, and then only afterwards restrict to rational numbers. Okay, so what is an extended rational number? It is just an ordered pair AB of integers. An ordered pair AB of integers where there's no condition on A and B. B does not have to be non-zero. And we're going to write this ordered pair in this fashion, and we're going to say A over B. Okay, as we proceed, probably often we will use a horizontal bar instead of a slanted bar, but officially it's A slanted bar, B representing this extended rational number. And part and parcel of the definition is this important notion of equality. When are two such expressions equal? This is exactly the same kind of thing that we did when we introduced rational numbers. We'll say that A over B equals C over D precisely when AD equals BC, and at least one of A and B is non-zero, and at least one of CD is non-zero. When we were doing rational numbers, we also had exactly the same kind of thing, but we didn't have any of this. We just said AB equals CD precisely when AD equals BC. Because for rational numbers, one of these is always non-zero. One of these is always non-zero. But here the possibility is that we might have A and B both being 0. We do not want to say that 0, 0 is equal to anything else. So for example, 2 over 3 is equal to 4 over 6 because 2 times 6 equals 3 times 4. 3 over 0 is the same as minus 2 over 0. Why? Because 3 times 0 equals 0 times minus 2. This is valid because both of these are not 0. Both of these are not 0. 0 over 7 is the same as 0 over minus 24 because 0 times minus 24 is the same as 7 times 0. This is our way of grouping together all the elements on the line to form one single guy. And the purpose of this qualification is to avoid making 0, 0 lie on every line. If we didn't say this, then 0, 0 would be equal to everything, because 0 times this always equals 0 times this, no matter what this is. But we're going to use this stipulation so that 0 over 0 is not equal to 2 over 3. 0 over 0 is not equal to 5 over 0, and 0 over 0 is not equal to 0 over 4. We want 0 over 0 to be something separate. So that's the extended rational numbers as objects. That's what they are. That condition of equality can be restated. So another way of expressing the equality between A over B and C over D is to say that it occurs when M times AB equals N times CD. These are the integral points for some non-zero integers N and M. I'm going to leave that as an exercise for you to think about, that the condition can be restated in this way. Okay, so now we have extended rational numbers. We want to define the operations. And here are the operations. A over B plus C over D is, no surprise, AD plus BC over BD. A over B times C over D is AC over BD. A over B minus C over D is AD minus BC over BD. And A over B divided by C over D is AD over BC. So we're taking the four operations from integral points and just transferring them directly to the teens, to these extended rational numbers. So we must check now that these operations are well defined, because after all, the names for the extended rational numbers are not unique, just as the names for rational numbers are not unique. So just as we had to check that the operations for rational numbers were well defined, we have to check that these are also well defined. And for that, it comes down to the homogeneity laws. The fact that when you multiply both A and B by a scalar, then this thing is not changing, and the form of the product means that that scalar is again appearing here and here in the same way, so we're getting equal numbers. So please check that these operations are well defined, and you might like to write down the laws of arithmetic that we get. I'm going to do that next time, but it's probably a great exercise for you to write down the laws of arithmetic, which include the laws for rational numbers, but go beyond to also include these new objects that we've got now. So we have two new objects which are not familiar rational numbers. We've got 1 over 0, and we've got 0 over 0. And we're going to give this thing a name, sort of a separate name. We're going to sometimes refer to it simply as infinity, the figure 8 lying on its side. So the infinity here has a very precise meaning. It corresponds to the extended rational number 1 over 0, which corresponds exactly to the horizontal line in our picture of integral points. Yeah, so just go back to the geometry. There's nothing ambiguous about this thing at all. It just corresponds to the horizontal line as opposed to some line with some vertical direction. And we have this special point, 0 over 0. We're going to also give that a new symbol. We're going to refer to it with this little star. I think that's a good symbol for it because it sort of represents the fact that it's the meat of all these lines. Okay, so that's going to be the symbol for 0 over 0. But what should the name for 0 over 0 be? Well, I don't know. And so I'd like to suggest an interesting challenge for you, is to suggest an appropriate name for 0 over 0. All right, so maybe in the next few months we can have a think about that, and then we'll collect all the various suggestions and we'll decide on a new name for this new mathematical object. We're extending mathematics in a direction that perhaps has not really been looked at least not too much. And we're going to be interested ultimately in extending not just arithmetic, but maybe also analysis to this larger domain. So next time we're going to have a look at the laws of arithmetic with these extended rational numbers. We're going to look at how we get the rational numbers from the extended rational numbers, and we're going to think about visualizing these things in practice. How do we actually draw infinity on the page? I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.